Saxon Advanced Math Lesson 74. This is dealing with Cramer's rule. Before we can get into Cramer's rule, we've got to do a little bit of review. I did put up there lesson 62 for review on this because I am going to go through the first part a little bit quicker, mainly because you do have a video in lesson 62 you can jump back to if you need to on abstract coefficients. But I've got I've got a system of linear equations here, and I'm going to solve for x. I'm going to multiply this one by d, right, to get that the same. This one by negative b. When I do so, I'll get these, and I add them up. I end up getting x by itself, de minus bf and dA minus bc. If you need to go back, I do this very quickly. I did show the work up here. If you need to pause the video and look at that, it is how we've done abstract coefficients before, or go back and watch lesson 62. I can do the same thing for y, and I put that here. Once again, I'm skipping the math on this. It's a little different than what I usually do. I usually go in depth, but it's a little longer video on the abstract coefficients, and I didn't want this video to be too long. So if you're struggling with that, stop the video, go back and watch lesson 62, because it does show you how to do abstract coefficients. We're going to start with these two values here, and I want us to notice something. These two values are unique, because I can look at this and say, if I had this array like this, I would say E times D minus F times B and A times D minus C times B, and I would have these two things. So in other words, I could represent these in a matrix. And where did these numbers come from? We're going to get into that in just a moment. E came from above, right? F came from above, because I'm solving for x, and then B and D came from these two. Now, let's just get into Cramer's rule, because this is going to look really confusing to begin with. But let's get into Cramer's rule, and we'll see how we're going to do this. In Cramer's rule, we're going to be able to solve real linear system of equations without having to actually work it out. This is a pattern, and this is named after some of the work that Cramer did. But the patterns that exist that work every single time allow us to eliminate the variables and put them in a matrix array. And matrices allow me to do so and then find determinants and use those determinants to find real answers. Watch carefully as we do this. First of all, I'm going to put this right here, and I'm going to realize that this 3 and 4 came from here. 2 and negative 3 came from there. And I just want you to just take a minute and realize where that's coming from. So all I've done is use a 2 by 2 square matrix, right? And I've said every coefficient value gets placed in exactly where they were. If I were to erase the x's and y's right there, I would have this array. And that's really all I'm doing. Now, when I'm solving for the x value, I'm going to use the y value coefficients like normal. There's my y coefficients. However, I'm going to take these two right here, and I'm going to put them right there instead of the x coefficients. So instead of it being 3 over 4, it's going to be negative 1 over 10. That's the only difference. So I'm taking this matrix, I'm duplicating it up here, but I'm crossing out the x values and plugging in these. And we'll come back to that in just a minute, why that's so important. Then I find the determinant. Negative 1 times negative 3, 3. Minus 10 times 2, 20. Over 3 times negative 3, negative 8. 4 times 2, 8, and I'm subtracting. So I'm going to end up with, when I substitute this out, x equals 1. This allows me to find out what a linear equation's x value is by using matrices. And it's very cool. Now, let me go back to where we started with, and we'll look at where these are coming from. Notice that all we did here was solve for what x is. And x happens to be whatever dE minus BF is over dA minus BC. If you'll notice where these are coming from, here is B and C, right? B and D, right from there. Here is B and D, right from there. There is A and C right from there. So all I've done is written it with these 4 numbers coming from these 4 coefficients. And then I'm doing the same thing on the top, but I'm substituting in for the value that I'm looking for. When I'm looking for x, I use these two. When I'm looking for y, I use these two in the place of the y value coefficients. And it gives me this right here without having to go through all the individual steps. I don't have to use substitution. I don't have to use elimination. I'm not graphing anything. I'm just getting an answer, and it works. So let's look at the y values matrix here. So y, notice that the denominator is the same. Well, guess what? So is the denominator the same when I work it out with abstract coefficients. That's interesting. So I'm going to use the same matrix array, right? And I'm going to look at this, say 3, 4, 2, negative 3. 3, 4, 2, negative 3. But in the numerator, I'm going to use the x coefficients, 3 and 4, just like I did before, right, in the bottom. But on the top here with the numerator, instead of using the y coefficients of 2 and negative 3, I substitute in that negative 1 and 10 again. That's where these came from, right? Now I use the same idea, so 3 times 10 is 30, minus 4 times negative 1 is a positive 4. 3 times negative 3, well, guess what? It's going to have the same denominator. 3 times negative 3, negative 9, minus 4 times 2, which is negative 8. And when you solve this out, the 34 over 17, or over negative 17, you're getting negative 2. And we're able to solve this system of linear equations using this method, and it works every single time. And this method is called Cramer's rule. Now, we've got to cover just a couple of things that could happen. When you're doing Cramer's rule, you have to remember that these are systems of linear equations. And systems of linear equations have 3 possible answer sets. If you remember that 2 lines can cross once, they can cross no times, which on a plane we call that parallel, or it could cross infinitely, where it's the same line. I think we would notice if these were the same line, but example 74.3 is not the same line. 3x plus 2y equals 5, and 3x plus 2y equals 8. For those of you who are still, you'll recognize that those lines are parallel. They just have different y-intercepts. So when I start plugging this in, I end up with 3 and 3 go here, 2 and 2 go here. The 2 and 2's for the x value, right, on the y coefficients are inserted, but I use 5 and 8 here. So once again, these ended up in for the x coefficients. Everything else stayed standard, just with the coefficients that they had, because we're solving for x. When you do so, you will find out that in the denominator, 3 times 2 is 6 minus 6. This is our problem right here. That's why I already have the word problem written underneath it, because I can't divide by 0. Well, as soon as I have a denominator that's giving me a 0, one of 2 things are happening. Either A, I made a mistake, which is what I always check for first, or B, they don't cross. And there is no solution to this because division by 0 is not allowed. It wouldn't matter what I did, and since I know the 2 denominators are going to be the same, right, because the matrices have to be the equal on the denominators on x and y, I don't even need to try the y value to know that I'm going to have division and 0 in there as well, and I can immediately stop and say the 2 lines are parallel. They don't cross. There is no consistent solution for this system of linear equations. These 2 lines are parallel. So this is Cramer's rule. Just to recap for you, when you're doing Cramer's rule, you're taking the coefficients and plugging them in the denominator in exactly the order they're in. When I'm solving for x, I use the equal number, the constant number. When I'm solving for y, I use the y's values in the coefficient instead. I use the constants in the y value coefficients place. But everything else stays the same. And then I use the determinant, divide the determinant over the determinant, the top and the numerator and the denominator, and I end up with 2 unique solutions, x and y. And sometimes it could be, x and y could be the same value, where they cross was 2, 2, and you will get that. And that's fine. However, this allows you to solve systems of linear equations without having any other work done. Now, just looking forward and thinking through, we already know that when I have 1 variable, I need 1 equation to solve it. If I have 2 variables, I need 2 equations. 3 variables, 3 equations. And this works on a 3 variable. So, and you've had those before in the beginning of the book. We had x, y, and z problems. And this will work exactly the same way because it is a 3 by 3 matrix. And anytime you would have the same number of rows and columns, you can use a determinant. That's one of the prerequisites to using a determinant. And so this works. This would work with a 4x4 or a 5x5. You think of how much time this would save in a 5x5 matrix rather than taking and using substitution 7 or 8 times or whatever it takes to get you to solve that out. This would allow you to do it in just a couple of simple steps.